going to talk about subdiffusion and Lévy walks, so about anomalous transport. Actually, the classical theory of anomalous transport involving subdiffusion, superdiffusion is well developed, and this is a linear fractional equations. But the question arises how to organize interaction between particles performing anomalous diffusion, like superdiffusion or subdiffusion. And this is a still open question, how to extend classical linear fractional equation to the non-linear case involving particle interaction. Of course, it's important for biology. In biology, the particle, especially in dense environment, always interact with each other. And I'll give you plenty examples from biology as a motivation to study non-linear fractional equations. Right, this is done work collaboration with Stephen Falcone, it's my former PhD students, Nikolai Korabel, my postdoc, and Peter Straka, who left me recently for Sydney, of course for obvious reason, from Manchester. And first let me give a brief outline of my talk. So because here that's not expert in anomalous transport, that's why I decided to give a brief outline of anomalous transport like subdiffusion, superdiffusion. I will give a physical, biological reasons why instead of diffusion we have subdiffusion and how to describe this subdiffusion or superdiffusion processes in terms of mathematics. And then second part of my talk, of course, concerned with nonlinear fractional PDEs. First, I will discuss subdiffusive Fokker-Planck equation as a motivation, which describes so-called anomalous aggregation of the particles or cells. Then I consider also particular problem of degradation and subdiffusion of morphogens. And then, by using this example, I will show you how to derive non-linear fractional PDE. And at the end, subdiffusive transport in two-state system. Because in biology, there is too many systems with a so-called two-state systems. So particles then move, then the rest, they change their behavior or phenotype changing all the time. So it's plenty example from biology. And the question is how to describe this two-state system in anomalous case. So that's my plan. Right. Well, this is just a reminder. Well, when we have a standard Brownian motion, of course, if we take expectation of position of the particle squared it, it's a linear function of time. This is obvious result, and macroscopic equation is trivial, diffusion equation. For subdiffusion, if we have a position of particle x and we squared it and take expectation, then t to the power mu. Mu varies from 0 to 1. So that's a subdiffusion. So at first glance, it's no big difference. You see, this is linear function, this is sublinear, but in fact, a macroscopic equation for the concentration of particle performing subdiffusion is quite different. And it's changed character completely because this is Markovian equation, but the equation for subdiffusion is non-Markovian. So it means involving integral over time. So this is just an example of fractional differential equation. So it just looks the same as this one, but now here, look, we have operator. We call it Riemann-Liouville derivative. And although it looks not very nice because it's very complicated, but in fact it's not, because here we have just convolution of the density with the power law kernel, and we just integrate it, of course. So this term, because it involves integral over time, involves memory effect, and this is a standard fractional partial differential equation explaining subdiffusion. Also, there is a superdiffusion. If this anomalous exponent mu is greater than 1, we'll call it enhanced diffusion because the propagation is faster. We call it superdiffusion. And again, a lot of examples from biology. Cancer cells, intracellular transport along microtubule inside cell, animals dispersal, obey this law in many, many cases. So it's a lot of review, and I will show you just two examples, like anomalous dynamics of cell migration. A lot of papers on why we have a superdiffusion for the transport. And this theory, of course, is well developed. And now the question is how to extend this linear fractional equation to a non-linear case. And this is non-trivial. And believe me, I will show you many examples which illustrate that.
By linear, you mean linear in row?
Yeah, of course, linear in row. For example, why it's non-trivial? If I write down standard fractional equation for the row, like this one, so it involves, of course, second derivative operator, and inside we have this fractional operator, 1 minus mu rho. Mu anomalous exponent. This is very important parameter, so please remember. Now, if I want to take into account, for example, this process, the degradation or production, can I put nonlinear terms on the right-hand side? The answer is no. So if we have standard Laplace operator, that's easy to take into account anything like reaction, death process. You just put on the right-hand side reaction term. But why additive? If we have here fractional operator, we can't separate anymore transport and reaction. That's the main idea. And then the question is how to take into account reaction. Then you have to start with microscopic model from random walk model and then derive microscopic equation. And I will show you that it will be very complicated combination of transport and reaction. So it's not additive. This is just one example why it's not easy. It doesn't matter just one equation. If you write down two equations or three equations, you can't simply, as before for reaction diffusion system, add reaction or death process and then study traveling waves or Turing instability, name it, so many processes. That business doesn't work for fractional equations. I'll give you examples today. Right. Yes.
You will show us why it is so, why you cannot add these together?
That's my main purpose today, to show this. Of course, it's not like a teaching, oh, shouldn't do this, forget it. No, I will show you how to do it and explain why you can't do this like that. This is wrong.
You have to push it at lower.
Yes, I will delete it because it's not good.
No. You go forward. If you want a screen.
Right. So this is just one example of subdiffusion. This signaling molecule in spiny dendrite. This is actually inside our brain. And this is experiment that the particle inside this structure behaves like this. So expectation of the position of squared is sublinear. And that's a very important parameter mu, which varies from 0 to 1. So now I need to explain why we have subdiffusion. What is the reason of subdiffusion? What is the physical idea behind subdiffusion? For this reason, let us consider random walk. So random walk in 1D. So we consider one-dimensional space. We divided this space like a lattice, typical size, let's say A. And particle symmetrically jumps on the right and on the left. So if we consider standard random walk theory, we just defined escape rate, lambda. So this is the rate at which particle escape from that position to the neighborhood. And of course, lambda escape rate determines mean time the particle spent at this position before jumping. Of course, this 1 over lambda. Now, if you formulate Mast equation and then take a limit when the size of this lattice tends to 0, you will end up with a classical, standard, trivial diffusion equation we like. So, and then, what is more, you will get explicit expression for diffusion, a squared over 2 and divided by mean time. That's what you will have. Now, this is a standard case. Diffusion. What happened now with subdiffusion? Again, one-dimensional case for simplicity. We have a particle sitting here, and this particle, of course, escapes from that position, position x. And we again define escape rate. But now the change is escape rate is not a constant, but the function of residence time. So the particle spends some time before jumping, and we call this random time is residence time. Here, residence time distributed according to exponential distribution. But here, lambda is a function, and it looks like this. So it's inversely proportional to the residence time tau. So the idea is the longer particles spend at this point before jumping, the less likely it escapes from that position. And if mu, now pay attention because that's the main point, if this parameter mu varies from 0 to 1, this power law, escape rate, generate power law waiting time distribution in a such way that the mean time t equal to infinity. So there is no characteristic microscopic time for this particular problem. And if mean time is infinity, what about diffusion? The whole concept of diffusion and diffusion equation breaks down. So this is actually a result of a violation of central limit theory. So the answer to your question, if the particle spent in this position and the distribution of waiting time or residence time behaves like 1 plus mu, so it's power law. If you take the distribution of residence time with this law, you can't integrate it like first moment. The first moment is divergent. So that's the reason of subdiffusion. And if you do proper calculation with this random walk model, you will end up with equation I mentioned, subdiffusive equation. So I hope that's very clear picture why we have subdiffusion. Okay, I'll give you an example, like from academic world. Like, if you are a postdoc, you're just jumping from one position to another one. Meantime, around 1 year, 2 year postdoc. But if you are a professor, you will trap here. And the longer you spend in that position, the less likely you escape. Because of mortgage, promotion, many other things.
What is the tau zero that you have?
Huh?
What is the tau zero?
Oh, tau zero is just constant because it should be dimensional constant. So this is the idea of trapping. If you are trapped somewhere and then the situation is better and better, then it's subdiffusion. The same for superdiffusion. But this is just another example. What happened when we have mean square displacement proportional to the t, and this parameter mu now greater than 1? Why we have enhancement? For the same reason. If, let's just imagine the cell movement. Just imagine, I'm a cell, I'm just moving with constant velocity in this direction. And then standard hyperbolic model, persistent random walk model say, oh, you have the rate of change of direction. You know this model, the classical one. You change direction, and then switch. And if you move back and forward, you will end up again with a diffusion equation with hyperbolic correction. But now imagine the cell. It moves in this direction. why should I change the direction? And if it's good direction, I just keep it. And the longer I stay in one direction, the less likely I escape from that. So with the same rate, but in different situation, these create superdiffusion, very persistent random walk. And that's what observed. And some people believe that this superdiffusive is a good strategy to find the food. If you want to find the food, your animal, you just move in one direction, and you should be very persistent to move in one direction. Don't change the direction according to Poisson law with a constant rate of change. So the rate of change depends on the time you spend in movement in one direction. So again, I've tried to explain the idea behind superdiffusion. The mathematics is quite complicated because it's non-Markovian process. And still equation for superdiffusion is not available. So any questions regarding subdiffusion? Because now I'm going to write down a lot of mathematics.
Well, there are a lot of models that give formally something non-diffusive behavior, but not this without this integral. Say a simple situation when you have a diffusion in a free space and traps, and this also will give you something with power less than one, but it is more natural to describe it differently by two equations and not by this integral equation.
Oh, that's true.
Then otherwise you can have the same two interacting phases, and there will be a flow in one of them.
Yeah, exactly. So that's
but again, you probably can formally reduce it to such integral equations, but of a different kind. So this model that you describe, it is perfectly applies to the example that you described. But there are great many physical examples when you have the same effect, but the natural description would be different.
Yeah, it's not just different, it's sometimes easier because that's a standard set. Oh, I don't like fractional equation. So instead of these fractional equations, let us write down this like trapping, and inside this trapping I could create 3 trapping or 4 trapping, and every traps has a Markovian property but with different escape rates. And then if I got escape rates as a sum of exponential, then it might create in a similar behavior as subdiffusion. That's right, there's a theory of that. So in fact, the power law can be approximated by 4 exponents quite easily in terms of experiment with the different escape rates. So this is just equation, but this equation got a lot of positive things. It's think theoretically, not just to explain some data from physics or biology. If you create a model, random walk model, and write down master equation, then you can create a lot of random walk models, and you can write down many master equations. And then, if you apply parabolic scaling, you will end up with a diffusion equation. Diffusion equation is like attraction point for many models. But then, if you create models corresponding to subdiffusion, subdiffusion equation is like attraction point for many other models. And then, because it's attraction point, so all models reduce to 1, this model has a very nice symmetrical properties. Symmetry, scale invariance, so it's a very nice object. It's not just to describe some phenomenon. It's a beautiful mathematical object and physical object. Although some data you can explain by very simple mathematics, of course. You don't need these complicated things. That's right. Anyway, this is a matter of philosophy. Okay, this is just Lévy fly. There's a lot of confusion sometimes. Lévy flight, Lévy walk, what's the difference? So it's a huge difference. You can't say, oh, this is Lévy flight and then change to Lévy walk, because I'll show a picture. So this is typical trajectory of Lévy flight. We have a particle, it perform random walk, and then jump long distance. And then again, fluctuate, moves, and then jump long distance. And this distance actually distributed according to the power law. So if you plot.
Sorry, so the Lévy walk are more related to the superdiffusion, not the sub.
Lévy flight means infinite second moment. Lévy walk is a superdiffusion. And that's why I'm trying now to explain the difference between Lévy flight and Lévy walk. So for Lévy flight, the animals move this distance instantaneously. And if you move instantaneously with infinite speed, then you will end up with this fractional equation for Lévy flight. This is Markovian equation. So instead of Laplacian, you've got some fractional operator. And the reason why we have fractional operator, because if you consider distribution of flights, then it looks like 1 plus alpha, where alpha varies from 0 to 2. So second moment for this distribution is divergent. And because second moment is divergent, you can't apply central limit theory. So you don't have a Gaussian distribution anymore. And at the end, you will end up with this fractional equation. But that equation for Lévy flight is trivial because it's Markovian. Lévy walk is different. Physically, the particle or cell moves this distance with finite velocity. And if you take into account this finite velocity of propagation in one direction, then it's a Lévy walk. The same distribution, but with finite velocity. And the equation becomes very complicated. In reality, of course, everybody moves with finite velocity. And that's what we call a Lévy walk. So it shouldn't be confusion between Lévy flight, instantaneous jump, long distance, and Lévy walk, when you move in one direction for a long time. That's the difference. Anyway, today I'm going to talk mostly about subdiffusion, although mentioned at the end. Now about mathematics. Of course, if we have subdiffusion, we need a basic equation for subdiffusion. And this is a standard fractional Fokker-Planck equation for subdiffusion. So let me explain term by term. We introduce the function p, the function of the position and time. So this is a standard probability density function to find the particle in this interval at particular time. And the rate of change of this particle depends on two terms. So this is classical drift term, this is a diffusion term. So the difference between standard Fokker-Planck equation and the fractional is just this operator, d. And this is famous Riemann-Liouville derivative already in terms of convolution. Now, if you are familiar with standard Fokker-Planck equation, if let's say particle or cell move in some external field or chemotaxis field or external force field, then this equation without derivative, Riemann-Liouville derivative, explains the rate at which arbitrary distribution converges to stationary state. So stationary state can be like Boltzmann distribution in physics, or some pattern or aggregation if some biological problem is concerned. So the rate. And Fokker-Planck equation usually give us exponential decay. So exponential rate of convergence. That's what we teach our undergraduate students when we separate variables, for example. But if we take into account anomalous effect, subdiffusion, then we have to use this operator, and the rate of convergence actually power law. You see this anomalous exponent. So not exponential, but very slow. That's what people believe so far, that fractional Fokker-Planck equation gives you a convergence, but very, very, very slow. Paulo. And recently we asked ourselves, because of biological motivation, drift parameter is function of x. Diffusion here is x. Why anomalous exponent mu is a constant? What do you think? Why is anomalous exponent a constant? Because it's easier to deal with mathematically. Of course, you see, standard Fokker-Planck equation involves two parameters, drift and diffusion. That's it. So locally it means Gaussian. But if we take into account subdiffusion, we have third parameter, mu, anomalous exponent. And if you make this anomalous exponent function of x, it's impossible to solve this equation. You can't introduce Caputo derivatives and many other things.
You write diffusivity as a function of x.
Yes.
And here, if it was a normal diffusion equation, you wouldn't write it like this.
No, of course. It is
you
just.
would write d over dx over.
It's up to us the way we write. If you write down in a standard Fourier law, then you will get extra term corresponding to extra convection. This is a standard way to write down Fokker-Planck equation in probability theory. Of course, it can be converted to divergent form in a standard way and you define the flux. So that's not a problem. This is a matter of description. So it's easy. But anyway, we just try to take into account the dependence of mu on space. And I'll give you an example. Of course, this is just numerical simulation. So we decided, okay, anomalous exponent is not constant, it's function of x, and it's just less than 1, and then we just say, oh, small perturbation, like this. And we try to understand what happened with the relaxation of arbitrary distributions toward stationary, like Boltzmann distribution. And what we found is the following. So this is a standard case of numerical simulation. This is, of course, a Gaussian standard Boltzmann distribution. But when mu is not constant, I'll give you this example, everywhere from 0 to I, and this is like 100, we put, of course, cells, everywhere anomalous exponent 0.5, apart from 1.42, anomalous exponent was 0.3. And what happened, all particles converges not to the stationary distribution like this, but they converge to this point, 42. Very slowly, but all particle aggregates at one point. And that's what we call anomalous aggregation. So at the beginning, we thought the equation is not good, Fokker-Planck equation. But then we started to think, oh, probably it's a good application for biology when particles have a tendency to aggregate at one point because of trapping. Because if what biological reason why we have anomalous exponent at some point different from others? So it's just more stronger trapping. If we say the rate of escape everywhere is different, for standard Fokker-Planck equation or for standard chemotaxis equation, you always have some aggregation phenomenon, apart from chemotaxis collapse. But here, you slightly change the property at one point, and all particles, I would say, all bacteria or cells started to aggregate at one point. Because it's good position or strong trapping, but that's phenomenon. And so there is no stationary distribution Boltzmann-like. Yes.
If the diffusion would have been normal everywhere, but only in that small region, it would be anomalous, just there. Not anomalous everywhere, but a different anomalous.
Good question, yes. It attracts all points.
It would still
Yeah.
work.
Whatever force, external force, so the standard Fokker-Planck equation, again, if you just one region with a strong subdiffusion, this region will attract everything. That's a numerical
So you can have normal diffusion outside of it.
Yeah, no problem, yes, that's right. So it's a very strong effect. So my point is, when we discovered that, of course, the standard application of subdiffusion is that mean square displacement is just sublinear. This is a famous effect for subdiffusion. But if you consider this subdiffusive effect on finite domain and consider aggregation phenomenon, it's so strong. It attracts everything. And then we decided, oh, probably linear equation not good. Because if we have all particles here, there's no oxygen here. So we need to take into account nonlinear effect. Particle to start interact with each other to escape from that position. And there's many phenomena. That's what I'm going to discuss right now. So that's a quorum sensing phenomenon, very famous in biology, when the motility of particular cells depends on the local density at particular point. Of course, the cellular adhesion or very famous volume filling effect, because the dependence of cell motility is on availability of space in crowded environment. So if we have a point at which we have strong anomalous trapping, because of volume filling effect, there is no space to attract particles. So that's what we take into account recently with Peter Strack, and we published this paper, Theoretical Biology. So many equations, quite complicated. If you now the time to show you why it's difficult to take into account reaction terms together with anomalous transport. That's what I'm going to show.
Could you comment about, is this model conserved? Do you use how do you derive the model from first principles?
Oh, you just got finite number of particles, you just, doesn't matter.
Is there any do you use any laws of conservation?
No, it's just random walk theory. Okay, my point is, let me explain. So in the past, it was easy to find macroscopic equation by using phenomenological law. You just use some common sense idea of conservation of particles. You write the flux of particle proportional to the gradient, or you can use hyperbolic correction and write down equation for flux. My point is, this breaks down because if it's subdiffusion, it's so difficult to write down phenomenological equation. You have to consider all the time microscopic model. You can do this, of course, and that's many theory. I'll give you an example. If you look at this equation, I just Laplacian. And if someone say, oh, now let us take into account nonlinearity. Now D become function of U. Of course, you will stop to talk to this person because it's contradict many things. Because it should be inside. But nowadays, people do the same for fractional business. Because they've got anomalous exponent and they say, oh, now this anomalous exponent depends on rho, on density, and just study this equation from pure mathematical point of view. It's not a good idea. You have to derive all these fractional equations from first principle, and this is continuous time random walk theory. So if you formulate random walk model, then you have to formulate master equation, and that master equation later on should be considered in continuous limit, and then you will get a proper equation. I'll give you an example right now. This is famous example of morphology gradient formation. So this is a classical problem. Let's say molecules are produced at some boundary, x equal to 0, an infinite domain, let's say constant rate. Then particle perform classical random walk, you consider the limit, you will end up with this equation. So it's standard diffusion equation, and then you just put minus degradation term. And of course, this equation has a very nice stationary solution. So you just put here constant delivery of particles. This is infinity. Sooner or later you will get some stationary distribution. And that is classical problem in mathematical biology, morphing and gradient formation. Of course, in linear case, when degradation rate independent on density, it's a trivial undergraduate problem for our student. It's easy to solve. If it's dependent, that's more complicated, but still can be solved. It's just power law. Now the question is, can we change this operator, second derivative with respect to space, to the fractional operator? The answer is no. If you formulate random walk model from first principle and do a lot of calculation, like master equation, continuous limit, you will end up with this equation. Look at the difference. So here, of course, you have the same thing, the rate of change of density with respect to time. But now look, this degradation rate appears inside transport operator like exponential factor. Here and here, in front of fractional derivative. And this is rigorous derivation of this equation. So the idea is that you can't split degradation term and diffusion as before. And if I ask you, can you write down phenomenologically from the very beginning this equation? Believe me, no, you can't. It's not easy. After some experience, yes, you can identify the flux, but again, this with experience. But also it depends on the way you model microscopically everything.
So what is the microscopic counterpart of the reaction? So you have to, that's my understanding at least, so you have to somehow represent the reaction on your random.
Right.
So
Okay, okay. It's a very good question. I was about to explain this and then you just asked. Right, because microscopically, in the past it was, if you have a particle, the particle have two choices, either jump or to be killed or die, right? Because you've got transport with degradation. So every process, if they're independent, got own times. Of course, here, theta is, if you just 1 over theta is characteristic time for killing, and diffusion coefficients also involves some microscopic time. But now, if you consider non-Markovian case, you also have two options, either to move or to die. And then, if you have a subdiffusion, the time you spend at a particular point might be very, very large. You're just trapped. So most likely, you will be killed before you experience long time of sitting at a particular point. And that's why macroscopically transport depends on reaction. Because let's say you are very old, you're just sitting and don't jump, you're just happy. And this is trapping subdiffusion. But then if there's possibility to kill, then you never experience of this power law distribution. It means effective cutoff. I'm trying to explain the physical reason behind. And then transport and degradation becomes not additive, they just work together. And in fact, it kills subdiffusion altogether. Because when we derived this equation, of course, we did not know what to do with this. Either to do Monte Carlo simulations, or just enjoy how it looks like. Because there is no method to solve this equation. It's very complicated because you see, it's not just here nonlinearity. Nonlinearity we have here. It's a very complicated way. There's a mixture of derivatives, fractional operator, exponential function. But in stationary state, when we are interested in this profile, because that's the main purpose of this equation, to find what happened in long time limit. What is the profile of morphology? And in stationary case, it reduced dramatically with a very funny effect. Now, please attention, because here it's a really interesting effect occurs. In stationary case, all this fractional derivative disappears because of killing effectively cut the power law distribution. and you end up with this equation, stationary equation for stationary density. But the effect is that diffusion coefficient becomes a function of stationary density due to this nonlinear effect. And this is dependent. So diffusion depends on density, and you see the power 1 minus mu, and still anomalous exponent. So effect is the killing rate enhanced diffusion. That's an idea. Have you ever seen in mathematical biology literature when the killing influenced diffusion? Usually diffusion is separate. Some microscopic model, rate of jump, size, and you define diffusion. Reaction has no influence on diffusion whatsoever. But here, if you take into account subdiffusive effect, effective microscopic diffusion in log time limit depends on density. And it's not depends on density, it depends on killing rate. That's important. You see, diffusion depends on this rate of killing. And that's the idea. Just imagine you have many particles with aging effect, okay? And they're almost all trapped. And the idea is, the longer you stay in some particular point, less likely you escape. How to enhance transport in this system? You just need to kill this old particle. That's an idea. Just kill them and give new particles with 0 age. And then you will create this distribution. That's a fact. This is just another non-linear effect of subdiffusion on transport process. So this is pretty new result. It's 2014, also with Nikolai. Oh, he just arrived. We look at diffusion dependence on external force with the same effect. When external force influences the particle, subdiffusive particle, and we have an effective transport. So this idea is not yet exploited in mathematical biology literature so far. So, any questions? That's an example why it's so difficult from one hand to take into account non-linearity concerning like degradation or production, and then with this interesting phenomenon at the end. Of course, the main idea is, if you have a particle which performs random walk and finally diffusion, you have to specify the age of this particle. If it's like exponentially distributed, there is no problem. But just imagine, we have a new particle, born, and then new born particle has to do random walk too. The question is the way you give them the age, and you will give different microscopic equations at the end. If you say we have a new particle and the age or residence time is 0, you will get one equation. And if you say no, we have a new particle just born, but they should have the same age as their parents. And then you will end up with different microscopic equations. That's a problem. It's looked like not universality, but regarding biological application, it might be a huge effect. Waiting time distribution or residence times are very important, as long as it's not exponential. So, in our modeling, we always have in mind our waiting time or residence time is exponential. And in this case, the model is Markovian, you've got diffusion equation. Otherwise, you've got non-Markovian models and problem like this.
What would happen if the degradation rate would also be dependent on the time of residency, for example?
Then you will have a mess. I've never even tried. Yes, that's of course, that's a standard model. The rate of degradation should depend on age. It should be increasing function.
Yeah.
Yes, that's right. Yes.
That
No, I have not exploited yet.
kill those
Yeah, yeah,
long-lasting.
Absolutely. No, that's a good question. I haven't explored this idea. You see, this is quite new. It's not just from 90s result. So it's still a lot of rooms to write good papers to explore this idea of interaction of subdiffusive process and nonlinearity. Right, I've got almost 10 minutes left. Yes?
Maybe 5.
Maybe even 5.
Yeah,
Okay, I skip.
some more minutes for.
Okay, just very brief transport in two-state system. Of course, in biology, switching between passive diffusion and active intracellular transport inside cell, it's all the time. You just particle have a diffusion and then move on microtubule and moves like ballistic in one direction. And then because of lack of energy, from diffusion state and then just switch over. And then this is typical for biology. Or it's just cell move in one direction. And then because of some reason, it switched to diffusion mode. And then from diffusion mode to ballistic again. And that happened all the time, switching between two states. Of course, if it's testing, you can introduce 3 states, 4 states, get PhD students, publish works, you know, that's not the problem. So many examples. Now the question is how to model this. In the past, it was, this is just another example, like smart tumor cells, they either move or proliferate, and there's always switching between movement and proliferation. Lack of time, and then let me explain. So if you have 2 states, you usually introduce 2 densities. One particles, let's say, they move, and another particle just proliferate. So this is an example. Let's say this particle, rho 1, with the density rho 1, they just move. And you put here operator. You can put here diffusion, advection, you can put integral term, whatever you like. It doesn't matter, just operate. And then imagine this particle, which is at rest, they know movement, they just degrade with this rate. It doesn't matter the form, it's just a particular case. Now, transport and degradation. You have to organize interaction between them. And what people usually do in mathematical biology literature, they put just 2 terms on the right-hand side, and this is just switching rate. You just introduce gamma 1, gamma 2, switching between 2 modes. This is Markovian model. It's a good model, but sometimes the switching occurs not according to exponential law, or not according to Poisson law. Why is that? Again, the reason why we use this switching, because it's easy to deal with. It's not just because of reality, it's just because of tractable model. And if the switching rate is non-Markovian, and this I'll give you plenty example why it's happening because of trapping, then you have to do something, and I will just give you, of course, final result. So if you do a lot of mathematics, everything, you will end up the following system. Still the same master equation, with the same operator, with the same degradation rate, but the switching rate are completely different. The switching rate is just integral over time and space, or memory and space effect, and like escape rate from the state 2 here depends not only on the density, but also depends on reaction rate. Or escape rate from the state 1 depends not only on density, but also on some property. This is just a green function corresponding to this operator. Depends on the transport. So my point is, everything is just interconnected. No superposition anymore. Because all the time we separate. This is reaction, this is transport, this is switching, and all of them are just different terms. Not anymore for anomalous transport. You have to start from, again, microscopic model, do a lot of calculations, assumptions, of course, it's inevitable. It's not like phenomenological way to write down many assumptions. assumption because it's a microscopic model. And then you will end up with a microscopic equation with very unusual properties.
Where is mu?
Huh?
Where is mu for the subdiffusion entering here?
Oh, here it's mu, it's inside this kernel, so I don't have time to explain everything. Anyway, some result, of course, in our book with Vicente, it's already old book, 2010, Springy series and Chinojak's reaction transfer system. Vicente here, me and Werner Horshemke. So, but now it's it's fast developing area, so it's already old material here. But if you want to learn something like what I described, that's probably a good starting point. Apart from other very nice review of anomalous transfer, I would recommend Lévy-Volk. So it's April-June 2015, Lévy-Volk review of modern physics. So it's pretty new, with huge examples of superdiffusion in many areas like physics, biology, human trafficking, social life, name it. Very popular nowadays subject, but we must be very careful. Thank you very much.
Questions?
Did you do anything about with super diffusion, not the subdiffusion?
Right, that's what we are doing right now with Nikolai. We've got some models with interaction between super diffusive particle. So within 2 weeks, we're going to publish on arXiv with interesting effects. Because super diffusion is more applications rather than subdiffusion. Even equation for super diffusion is not available. That's the point.
Any other questions? Okay, I guess we'll meet over our lunch if you have any further questions for you. So let's thank you.
Right, thank you very much.